Oh, hi there. This is Lewis Structures. So exciting, can't wait. All right, let's start with ionic bonding. So diagrams for ionic bonding, remember that our metal loses electrons. So when we're doing a diagram to represent this, we draw the symbol for our metal. We don't show any electrons because they will have lost electrons, lost those valence electrons. And then we do square brackets and a charge to represent the electrons lost. On the flip side, our non-metal, remember, gains electrons, so we actually show a full octet of a Lewis dot and square brackets with the charge. The example here is the sodium and the chloride. So notice that the sodium, our metal, the first one, has lost its valence electron. It would have come from sodium, first column, so one valence electron. So to become stable, sodium lost its electron, so we put the symbol in the brackets. And when it loses the negative electron, it becomes positive. And then chlorine is seventh column, so it has 7 valence electrons normally. Notice that the picture shows that the chlorine has gained its extra electron to fill its octet, and when it does that, it has a negative charge. Let's do another example. So let's do an example of, let's say, magnesium and partnering with phosphorus. So if I'm looking at magnesium, magnesium has 2 valence electrons. So that's the Lewis structure for magnesium. And phosphorus is in the 5th column. It has 5 valence electrons. When they get together, magnesium will lose its 2 electrons. So I'll put magnesium in square brackets without the electrons because I'm losing them. When it loses those electrons, remember electrons are negative, so it's going to become positive 2 for each electron that's lost. And then phosphorus is going to end up with a full orbital. Oopsies, my dots are having tricky troubles here. There's my phosphorus, so it gains 3, and when it does that, it has a 3 minus charge. Now this isn't balanced, this is just showing the charges that it makes, but we know for crossover purposes, we would need more magnesiums and phosphoruses than what we're just showing. We're just showing how they get together. Let's try one more. This is a great opportunity to pause the video and try this one yourself once I've shown you the combination that we're going to do. Let's do a lithium and nitrogen combination. So if you want to try it, pause the video and then come back and see how it plays out. Let's start with lithium. Lithium is column 1, stupid dots, so it has 1 valence electron. Nitrogen, column 5, 5 valence electrons. If I can put the dots in, oh my gosh, come on dots. Oh my goodness. Okay. And then lithium, again, is in column 1. It has 1 valence electron. It's going to lose that electron. So we're not going to show it in its picture here, and it'll be positively charged when that happens. And then nitrogen will gain 3 to become a full octet. If I can show you the dots, here we go. There we go. And because it's gaining 3 again, it'll have a 3 minus charge. Again, I haven't balanced it. I haven't shown how many of each, but we're just showing how each item looks. So we're going to walk away from ionic at this point, and we're going to focus our energy on covalent bonding next. And covalent is actually where we spend a lot of time when we do Lewis dot pictures because there's a lot more variety, whereas ionic bonding kind of is the same all the time. So remember, in covalent bonding, it's not an exchange of electrons like we just showed. This is looking at electrons being shared. So when we have electrons, we're only usually trying to pair electrons up to fill orbitals. Pairs can be shared between molecules once, making a single bond, which is the most common. They can also be shared twice, which makes double bonds, or even 3 times, which makes triple bonds. So you'll see all of these types of bonds being made when we do covalent bonding pictures. The bonding electron pair is the shared pair of electrons between elements. So this is just some terminology. A lone pair is a pair of electrons that's not in a bond. So this would be on the outside of an element, for instance. I'll give you an example here. Let's say I had an HCl and I had electrons around the outside of the chlorine showing the electrons here. The line represents the bonding pair, whereas the dots on the outside of chlorine are the lone pairs. Usually all elements are trying to achieve an octet, although this is not always the case. There's actually elements, there's one element, boron in particular, that likes less than an octet. We'll explore that more in grade 12. And then there's also elements that don't mind having more than an octet, and we see that occasionally where they'll have even more space for electrons. And again, that makes more sense in grade 12, although we sometimes see it in grade 11. So when we're drawing these pictures for covalent molecules, we're going to be following a set of rules. And if we follow the rules, it won't go wrong. It's when we deviate from these rules that we're going to get into trouble. So the first thing we would do is we're going to count the number of valence electrons on our compound using our column numbers. So I'm going to go through the rules first, and then we'll show this example. We're going to add electrons if we have a negative ion, and we'll subtract electrons for a positive ion. This count that we do is essential because this is going to show us how many electrons must be part of our picture, and this is always going to be an even number. If you count up your valence electrons and you have an odd number, something has gone wrong. Like let's say you get a 7. Something is missing. You should have either a 6 or an 8. So it's probably these ions that you haven't accounted for that will come into play sometimes, but you should always have an even number. Step 2, you're going to take your formula and you're going to put your unique atom in the middle and place the other atoms symmetrically around the central atom or the center atom. Unique just means one of. So for instance, if I had the example of CO2, which one do you think is unique? Well, the C is what we would call the unique atom here because there's only one of it. So unique doesn't mean like super cool. It just means that there's only one of it. All right, your third step is you're going to start putting electrons in as pairs. It's a little hard to see that I have bolded this word, but it's super important. Pair, remember, means 2. So you're putting electrons in as 2s. The first pair of electrons always goes between your central atom and each surrounding atom. You're basically going to connect the molecules, those elements, to each other. So the bonding pairs go in first, and then in step 4, you're going to continue with your pairs of electrons, but this time you're going to give octets to your surrounding atoms so that they're nice and stable. Remember that hydrogen doesn't need an octet. I've just put this in as a note here because hydrogen only has orbital 1 if we think about its Bohr-Rutherford picture. I'm going to do an abbreviated one here. Hydrogen has 1 electron already, and then it only wants 1 more for stability, so it's maxed out at 2. All other things that you're going to work with are going to want 8, though, so this will come into play. In number 5, this is the most crucial step. Mostly students do pretty well between steps 1 and 4, but number 5 is where it gets tricky because there's sort of different events that can happen. The first thing that you need to do is count how many electrons you've used up in the picture so that you can get an idea, because remember in step 1 you're doing an electron count for the whole picture. Let's say there's 18 electrons. In step 5, you may not have 18 electrons. So what you're trying to figure out in step 5 is, have I used up all the electrons? If not, where do they go? And if I've used them all up, is this picture actually complete? So the first job in step 5 is to count. Now, what happens once I count? So we've got a few different options here. Option A, if the central atom has an octet, I'm going to underline this because if it doesn't have an octet, we're not done. But if it has an octet, and you've used up all of your electrons, yay, you go to step 6. Step 6 is a good step. Oh, one-eyed happy face. Step 6 is a good step because that's your final step. So this is an occurrence that could happen. This is the best possible scenario. So remember, an octet is 8 electrons on your central atom. That can be a combination of electron pairs and bonding pairs, but it has to be 8 electrons. And again, you've used up all of your available electrons. All right, that doesn't always happen though. Let's have a look at what else could happen after you do your count. So let's look at scenario B. If the central atom does not have an octet and you have no electrons left over, oh no, I don't have an octet. We know our central atom wants an octet, but we have no more electrons to give. What we have to do is we have to shuffle around the electrons that we already have. So what this does is we create something called a coordinate bond. And this is when you share multiple times. And this will create a multiple bond. So if I share electrons between 2 things twice, that makes a double bond. If I share electrons between 2 elements 3 times over, that's a triple bond. So if I've run out of electrons, but I still have to provide the octet to the central atom, which I'm going to have to, I may have to just move electrons around to make multiple bonds. Totally fine. I can do that. All right, let's have a look at step C, or scenario C. If you have extra electrons, sometimes that original count, again, going back to the idea, let's say I did my count in step 1 and there's supposed to be 18 electrons on my picture. And in my picture, when I count them, the ones that I've placed, I only have 16. this would mean that I have 2 extra electrons that I'm supposed to put in that picture. The extra electrons always go in the same location, and that is the central atom. It's always going to be our focal point. One other thing that could happen is you can put those extra electrons in, but maybe you still don't have an octet. Then you're going to go back to step B, where you're going to make that multiple bond. And that sometimes happens as well, where you've got those extra electrons, but you still don't have an octet, but that's okay. Part B deals with that, make a multiple bond. So lots going on. Use the flowchart that I'm going to give you in class to help you with this as well. Let's try some examples together. Oh, never mind. Let's do step 6 first. So step 6 is when you have to redraw your structure. And this is where your dots that are between elements will become lines. So anything that is an electron pair between elements is a bonding pair. So again, we're going to use a line to represent bonds. And the lone pairs will stay as lone pairs. So you'll still see all those other dots. If the compound is an ion, so remember an ion is something with a charge, you would have accounted for this right in step 1 where you added or subtracted electrons based on the charge. You have an extra step. You're going to be putting square brackets around your picture, and then you're going to put the charge in the upper right-hand corner. So we'll do examples of all of this so you can see it in action. Now for realsies, it's time to make examples. So my first example is PCl3. I'm just going to redraw PCl3 down here because in step 1, we're going to do an electron count. So I'm looking for valence electrons. So my valence electrons for phosphorus is in column 5, so there are 5 valence electrons for each phosphorus. Then I'm going to add it to the valence electrons for chlorine, but I have 3 of them, so I'm going to do 3 times. If I have a look at where chlorine is on the periodic table, it's column 7. So I'm going to do 7 times 3 for 21, plus another 5 for 26 electrons. So in my picture, this account is going to be really important because if I don't do this correctly, the outcome isn't going to go well. So I have to have 26 electrons in my picture. That's step 1. Step 2, I'm going to put the unique element in the middle. In this case, phosphorus is my unique element because there's 1 of them. And then the others are placed symmetrically around the outside. So I'm just going to do it like this, although there's lots of ways to put it symmetrically. Now I'm on to step 3 where I'm putting electron pairs into the picture. So my electron pairs are always going between my central and surrounding atom to start. So these are my bonding pairs that I'm putting into place. That's step 3. Step 4, give octets to my surrounding atoms, my chlorines. So right now each chlorine has 2 electrons. I'm going for 8. So I'm going to have to put, these dots are going to be super annoying for both of us. And I'm going to put in 6 more electrons for a total of 8 electrons per chlorine. That's step 4. Now I'm on to the crucial step 5 where I'm counting electron pairs in the picture. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons in the picture. The other thing I check for at this point is an octet on my central atom. I do not have an octet. Sad face here. All right, let's have a look at the scenario. In A, I have an octet and I've used up all my electrons. This is definitely not an A. I'm supposed to have 26 electrons in this picture. I only have 24. B, the same thing. I don't have an octet, but in this case, I have leftovers, and so I'm actually going to do a scenario C. So I'm just going to write that here so we have it there. This is a scenario C. Scenario C means we have extra electrons, and because of that, I deal with those first. If I needed to, then I could make a multiple bond, but because I have extra electrons, I'm going to put those on first. Extra electrons always go on the central atom. I'm going to put my electrons right there. I'm going to make them big and obvious so they look like they're supposed to be there. And now my octet is complete, so now I'm happy. I've got my octet, I've got my 26 electrons, I'm actually ready to make my good copy. So in my good copy, all I have to do is I'm going to take out the electron pairs between, and I'm just going to replace those with a line. So those electron pairs are still there, we're just representing them differently. An electron pair as a line is a bonding pair as opposed to a lone pair. This is now my final product. Yippee! All right, let's try it all again. Again, I'm going to start by writing down my NO3- nitrate ion, and I'm going to do my electron count. So nitrogen is in column 5. Then we have our oxygen. There are 3 oxygens. Oxygen's in column 6. And then I have this negative charge, so I have an extra electron because of that. So I'm going to do my electron count. We've got 24 electrons that need to go into this picture. Now I'm choosing my unique element, which is nitrogen, since there's only one of it. Oxygens will go symmetrically around the outside. Again, lots of ways to do that. Let's put in those electron pairs. So the first pairs, as usual, this is step 3. We're putting them between my central atom and my surrounding atom, if I can make dots. There we go. And then step 4, I'm giving my octet to my surrounding atom. Stupid dots. I'm going to try my finger instead. That seems to be more effective. There we go. Perfect. And now we're on to step 5. So step 5, remember, I'm counting the electrons in the picture. When I can count by 2s, I can count by groups of 8, anything you like here. When I count, I've got 24 electrons in the picture, and I also have to check for an octet. So 24 electrons is a match, because I have 24 electrons that I'm supposed to have over here, but I do not have an octet. So again, frowny face for an octet. If I have a look, though, this is not the same as the last one, because the last one I had leftover electrons. I have run out of electrons at this point. So what I need to do is I need to use the electrons that I already have and just shuffle them around. Now, all the oxygens are the same. They're equivalent to one another. So all I'm going to do is I'm going to say, okay, oxygen, in order for everybody to get along, you're going to have to self-sacrifice here. You're going to have to move that electron pair into the middle so that you and nitrogen can share equally. That's fine. Oxygen does not mind doing this because it benefits both parties, because then we can make everybody happy with an octet. So I've got a little bit of work to do for this final picture. I'm just going to make some space because I'm going to redraw it, because when I do it this time, I'm going to have 2 bonds. Actually, let's change the color of that. Let's put the bonds in green. I'm going to have 2 bonds between one nitrogen-oxygen pair and then single bonds for the others. I'm still going to have the electron pairs that are untouched around the outside. So I'll put those in. And then I also have one extra thing to do. Hopefully you're thinking about it right now, but because this is an ion, I also have to put square brackets and the charge in the upper right-hand corner. So this is now my completed picture. All right, last example. This one is a little bit different because, again, I have my nitrogen, but there's only one element. We're going to see examples like this or where there's not a unique element. This is why I'm doing this example here. Let's start with our electron pairs, though, because we always start in the same place. There are 2 nitrogens. Each nitrogen is column 5, so a total of 10 electrons for my picture. This is where it gets tricky. There's no unique element. So when that happens, sometimes they share the unique position. And in this case, we're just going to say that one is the central atom and one is the surrounding atom, just so we can go through the steps. So we're going to do the steps as always. The first electron pairs go between central and surrounding. Let's assume the one on the left is considered our central atom and the one on the right is considered our surrounding atom. That means the next step is to give electron pairs to the one on the right. At this point, I'm going to count because I've followed all my steps. Again, we're counting the nitrogen on the left as the central atom, so I'm just doing the steps accordingly to that. I've got 8 electrons into the picture, so this is not a match. And if I look to see if my central atom has an octet, it is also not happy. So we have a little bit of work to do. The first thing I'm going to take care of is the electrons because I have extra electrons. So those extra electrons, remember, always go on the central atom, and I designated the left nitrogen as my central atom. So I've now fixed the first problem. I've got 10 electrons in my picture. I still don't have an octet though, and I've run out of electrons. So just like the last example, I'm just going to be creative and I'm going to move some electrons around. So I'm just going to put another pair in here. That would give this central nitrogen only 6 electrons though, so I actually also have to share a second time. So my good copy then, we're going to have our nitrogens, but we're going to have a triple bond between them. Each nitrogen will also still have an electron pair, and it doesn't really matter where you put these. I'm just going to keep them in the same position as they see above. This is now a happy molecule. Everybody's got an octet, and we've got our finished picture. So now it's time to work on a worksheet and have some fun.